Thanks, John, for the nice introduction. Screen set up here. All right, well, that was a really great introduction to Optical SETI from Paul. I'll be talking a little bit about one slice of the Optical SETI capability and discussing the Optical SETI with the Automated Planet Finder. So to give you a little bit of my own background, I've done a lot of high resolution spectroscopy with the California Planet Search. And during that time of sort of data quality manager, I realized years later what I was really just getting myself ready for was anomaly detections of high resolution spectra, such as those we're looking for with the Automated Planet Finder. So the Automated Planet Finder pictured here on the right is this is a nice fresh picture from this morning, nice sunny day on top of Mount Hamilton today. Is a 2.4 meter optical telescope, a traditional place for us to take our summer interns back when things like field trips were allowed. So to give you a really broad brush stroke of, here's a stereotypical high resolution spectrum, artificially colored. This is not an APS spectrum, but it shows some of the more famous Fraunhofer lines that are quite broad. They're the dark colors within the bright sections of this image. I've circled a couple of them here at the top: sodium D, magnesium B in the middle, and calcium H and K lines at the bottom. Of course, we get a lot more than just the Fraunhofer lines at high resolution. The Automated Planet Finder is a single instrument telescope with a Levy spectrometer having a resolution of about 100,000 in the middle of the optical. It's got broad wavelength coverage into nearly excuse me, into the near infrared, although there is some fringing that inhibits some of the searches at that edge of our spectrum. Here on the right, you can see some of those Fraunhofer lines, calcium H and K at the top, magnesium B, as well as a plethora of other spectral features, a lot of them from iron, but you can see that there's just spectral lines all over the place for this stereotypical solar-like star. This is Tau Ceti, a nearby star in the solar neighborhood. And what we're looking for with the Automated Planet Finder are spikes that fall above that continuum. So here's an actual spectrum from the Automated Planet Finder. You can see the wavelength going top to bottom, left to right. You can read this as sort of words on a page. You can see a lot of telluric features up at the top. Let's see if I can get my cursor working here. Maybe not. I'll attempt here. So at the top, you can see some telluric spectral features, these very regularly spaced features here at the top up here. You can see some of the weaker features now here at the bottom, sodium D in the middle here, H alpha. And you can see that while this is a nice bright spectrum of a sun-like star, if we, oops, I've disabled my ability to change the slide one moment here. Here we go, and a lower solenoid spectrum, which is more typical of breakthrough listen data quality. You can see some bright specks within the spectrum. Those are cosmic rays. This lower solenoid spectrum shows the cosmic rays better. And while the telluric features are still here, these are the two main sources of false positives for searching for narrow emission features from laser lines in optical spectrum. So here's a spectrum of a rapidly rotating star. You can see there's many fewer absorption spectral features, but these cosmic rays still stand out above the continuum. And when we do our laser search for things that stand out above this sort of average flux from the star, what we get is mostly cosmic rays and telluric absorption features, or sorry, emission features that masquerade as these signals that we're looking for. So to zoom in a little bit, here are some graphics from Lippmann 2017. And what we see here is the raw 2D image in the top and in the right of these plots with the single row profile plotted on the second plot. And what you see in this plot on the left is a very narrow spike caused by this cosmic ray. We can see there's only a single pixel being affected at 20% above the continuum and a few lower pixels. And this is one way that we discriminate between laser emission features and false positives like cosmic rays, because we require that the signals that we're looking for match the instrumental profile of the telescope, of the instrument. And in this case, our instrumental profile is about 3.5 pixels with the automated planet finder. And so we can easily throw this out on the left as a candidate because we can see that it doesn't fit the profile. So in order to fit the instrumental profile, the light from a star or surrounding a star has to follow the light path off of all the optics of the telescope and through all the optics of the spectrometer, and cosmic rays don't follow that light path, and so they don't share that same profile. On the right is a telluric emission feature, and we can see that it fills the vertical direction, that's the spatial direction, meaning that it's coming from the Earth's atmosphere, all of the sky that's visible at that wavelength through the spectral slit is emitting and filling the CCD with light. And while this does match the spatial profile, we can discriminate against this from a proper laser line search because it fills all of the sky pixels beyond the profile of the star that we can also see. So understanding the instrumental profile is really the main key to discriminating between spectral features, laser line features, cosmic rays, and telluric features. So going back to the anomaly detection that I was mentioning a little bit before, Nate Tellis, who's on the call today. Hi, Nate. This is from his paper, Figure 11. And this is one of those anomalies I was describing when we were taking the data at the telescope. This is from the high-res spectrometer and the Keck telescope, sort of a sister instrument to the automated planet finder. This shows, again, this tall profile, the vertical profile, filling the sky pixels on the CCD. And these regularly spaced features are from a collision of the K2 laser. We actually looked right into the artificial star created by an AO laser, and we get this nice cascade of regularly spaced lines near the sodium region. And this was a really fun one because everyone's looking at it. We didn't know what it was, or like, what do we find here? And then finally we figured out that it was a collision with the K2 laser. So this graphic on the right shows all of our typical issues that we can have when discriminating against false positives. You can see some bright colored cosmic rays, in particular one streaking left to right here. You can see these features that fill the entire sky. In this case, this is our optical equivalent of radio frequency interference, but this is much less common than typical emission telluric lines. And on this left-hand side, just another variety of false positives, telluric emission features modeled such that they can be discriminated against from laser lines. And this is some nice work done by one of our former interns, David Littman. So what kinds of stars are we observing with the automated planet finder? So on top of the typical stars that are observed with the California Planet Search and others who use the automated planet finder, while those surveys, we can use their data to search for optical laser lines. They typically focus on sun-like stars and stars that are slightly cooler, that have low activity and are slowly rotating. So with Breakthrough Listen, we take this approach where we make little bins out of the HR diagram. We try to get a few stars from each bin, including some giant stars, so some stars off the main sequence, in an effort to just get as large a variety of stars as we can, since we don't want to bias we don't really know where to look for SETI signals, so we'll try a little bit of everything. And so we've observed with the automated planet finder all the stars that fall in these bins that were chosen that were not already observed with the Keck telescope and analyzed by Nate Tellis in his papers. In addition, we've recently started collaborating with the TESS team, and in that effort, we've chosen targets that TESS identified as having transiting planet candidates. And for the automated planet finder, our sweet spot for detecting some of these lines, start detecting laser signals, is bright stars that are nearby. And so we've chosen planet candidates brighter than 10th, within 100 parsecs, and not false positives in some of those typical selection effects that we have. All right, and I'll mention that tomorrow night we'll hear about Veritas later in today or tomorrow, but we'll do some simultaneous observing where we have selected 4 targets from our TESS planet candidate list, and we have it scheduled so that we'll observe these 4 stars at the same time with both the automated planet finder and with Veritas, and that'll be experimenting with some new technology, new opportunity that we haven't yet tried, so that'll be fun. All right, so I mentioned something about the distances that we choose and the sensitivity of the automated planet finder. Here's a picture on the right of the TESS telescope. In choosing these targets, we're not only choosing the test targets that are the most nearby and accessible to the APF, but we're also choosing targets that have their ecliptic aligned with the Earth. And so in the Earth's solar system, almost all of our radio communication is transmitted within the ecliptic to our outer space probes and to the moon and things that fall within the ecliptic. And so we prioritize these test candidates because their own ecliptic is aligned with us. Perhaps there's some sort of communication going in between planets or their own space probes that we can capture. And so to just emphasize some of the things that Paul was discussing, at really the way that we detect laser signals above the really bright continuum of the star is we have incredibly high dispersion. Each pixel is on the order of 100th of an angstrom, and with that we can get to energies that are plausible for us to detect by condensing all of that energy into very, very narrow wavelength regions. And that's the key to optical SETI with the automated planet finder. So these lasers can outshine their star, but only at this very small wavelength range. Excuse me. So far we've had a great paper that was done by one of our student interns, David Littman, that was focusing on Boyajian star, of course, a famous SETI consideration target, although I think it's been confirmed now that the odd light curves that identified that started the whole interest in Boyajian star are confirmed to be astrophysical. It was really a fun target to have in our SETI world to focus on with the automated planet finder and other instruments as well. And so we took many hundred spectra of that and then looked for laser lines using injection recovery to test our sensitivity. And so we wrote those results up a few years back. Additionally, we took some spectra as a follow-up of some of the Bora and Tradier papers that came out a few years ago claiming periodic spectral modulations using DSS spectra. So we followed those up. We looked for those spectral modulations. We didn't find any. And so with these two papers, we like to we like to promote one of our roles at Breakthrough Listen is sort of a clearinghouse for SETI detections and showing that we can follow these up in the optical, and in this case, of course, we didn't find any. Michael Hipke also did a nice paper that was refuting these claims of spectral modulations as well. And of course, we're always working on the next thing, which is a comprehensive search for laser lines in the automated planet finder. As Steve Croft is going to talk about tomorrow, we have a really great internship program at Breakthrough Listen. Picture here is David Littman, who wrote that paper I mentioned before. He's now, as he did his work as a high school student, he's now an undergraduate at Princeton. And I'd just like to give a shout out to our 2020 intern, Anna Zuckerman, who worked on the automated planet finder last year and got a mention of the Chambliss Prize. And our two other interns who are coming in who will be working with me on the APF this summer, Malik and Zoe, and I saw Malik is on the line, so welcome Malik, and look forward to working with you this summer. Finally, I'll just mention that we have lots of exciting things coming up. We have a new offset guiding technique that we can use to get high resolution spectra of stars fainter than 10th magnitude. That's a new technology that we're working on with Brad Holden. I mentioned the simultaneous observations with automated planet finder and Veritas, which will be taking place tomorrow night. The observations of these test planet candidates are in collaboration with Daniel Giles, who's going to give the next talk, and Anne-Marie Cody, who are looking for test light curves for anomalies. And so with that, I will wrap up, and if there's time, take a quick question.